Hello there, welcome back to my channel. In today's video, I will be showing you how you could use FFT to filter images. So basically, we'll be going from an input image like this. It could be colored. In this case, I'm using a grayscale image of myself. So this is an input image, and we'll do a discrete Fourier transform. We get the FFT. So these are the Fourier amplitudes. Showing here the magnitudes of the spectrum. And then we'll filter out the low component of the frequencies given this panel. And so the middle, we're just blocking up the low component, and then we're keeping the high frequencies. And if we inverse this FFT back to the physical space, then we get something that looks like this. So this is the final output. We have effectively detected the edges in this image. Again, I will show you how to play around with this to get like just the features that you're interested in. So for example, there is like some stuff that look like blurry. We could fine tune this to get rid of that, and I'll show you that during the video. Alright, with that said, let's get started. Let me readjust this zoom. Looks like, yeah, I think that looks better. Hopefully you can see. So we'll start. Right from the start, we just need to import the required package. We'll run that. So we're just having OpenCV for reading the image. So I have the image in this folder called data, and I'll be using this called Ben, which is the image of myself. And we'll be using NumPy to convert from one space to another. So for example, our array, for us to do FFT in OpenCV, we need to convert it to, for example, float 32. And so this allows us to manipulate those arrays. And we have matplotlib that will allow us to visualize these images. So as I'm making the image going from one stage to the next, I will be making a plot so that you could see what's happening. And so at the end, we want to be able to reconstruct the image after it's filtered using the inverse FFT. Great, now that we've successfully imported, and you can know that by having a number. So we'll run this cell, and then we got this number here. So it means it has finished running. We have these packages, or these libraries loaded now. And the next step is to load the image. So as I said before, I have the image in that particular folder called data, which is this one. So I'm just providing the path to where the image is, and I'm specifying here as to read it as grayscale. Again, you could change this to 0. It doesn't matter. If you switch this to just 0, it will load the same image. If you set it to 1, it will load a color image. But then in this variable image, we'll load it, and it will be in this variable. And for us to do FFT, we need to convert it to float. So basically, we're just like changing it from unsigned integer 8, which is 0 numbers that are integers from 0 to 255, to float. So now they are more like they are float. They are not just integers. That's the data type that OpenCV wants from us for the discrete Fourier transform that we want to use to filter the image to work. So that's what we're converting. So we'll convert that, and we're calling this as the image float. If we plot either image float or the image, it will look the same. So I'm going to run this cell so we could look at the image. So just the image. Again, if you don't like the numbers, you could silence them by just saying axis off. Sometimes I like having that, so just run that again, and it will run it without the axis so that it looks like the way you have it in the phone. So that's the input image. Again, I said if you run this or if you run this, it doesn't matter, you get the same thing. So to show you that, I will just copy this and paste it here, and then change this to be image float. And if we run this one, so I'll comment the one we had before, we should have the same result. So if I run that now, yeah, we'll have the same thing. Again, go print the color map, the color bar to see the range of numbers to go from 0 to 255. So we successfully loaded the image that we want to manipulate. Our goal in this particular tutorial is to filter out the low frequencies so that we just keep on the high frequencies, and that way we could effectively detect the edges in the image. So let's get going. Now that we've converted our image, we'll have to do the FFT. It could do for FFT, or it could do discrete and Fourier transform, so DFT. So let's do DFT. Again, if you remember your complex numbers, once you do DFT, your output from DFT will be a complex number, which means it will have like a real component and an imaginary component. A real component will be at the first, the same way you write a complex number, which is always a real plus an I, some number, which the second part is always like an imaginary. So when we feed in our image, our output here would have two channels, and the first channel will be the real, and the second channel will be the imaginary. Just what you need to know. This is the syntax. Yes, the DFT is available in SciPy. It's also available in OpenCV. Since we want to minimize the use of package or maximize the use of package, we're sticking to OpenCV. So in OpenCV, if we say OpenCV.district transform, and then feed in our float image again. If you feed in just an integer here, you get some errors, so you don't want to do that. Feed in that, and then the flag they want to provide is to tell it that the DFT and your discrete transform and your output should be complex output. That's what we want to do. And if we run this cell now, we're going to have some result here. Maybe you could play around with checking what is there. It's just going to be some complex numbers, basically. So it has like a real component where it's not organized here in an obvious way, but it has two channel, and that's like contained this several bracket I was saying. So let me not kind of like mislead you or give you unnecessary information. Now we have done our DFT on the image. We have the result here. Next is to prepare a mask, so that we could be able to mask out the frequencies that we don't want. And to do that, or rather even before doing that, what we want to do first is to shift the frequencies. So when we run this, the 0 of your frequency, if you're already familiar with FFT, it will be at the corner, so the lower left corner, just like your Cartesian. It will be at the lower. We don't want it to be at the lower, so we'll always shift it to the center. And to do that, you use the FFT shift. So basically, this output of the FFT that we got here as complex number, we are feeding it into this FFT shift. So this or in NumPy, so FFT, and then FFT, there's an FFT shift. So it's what it does is just basically move your frequency to the center, so that you have at the center point is 0, up is positive, down is negative. It's basically the same way of Cartesian, but rather than having it at the corner, then you have everything at the center, which is a good way of visualizing it. So let's call that, after it's successfully shifted, let's call that shift as DFT shift. Again, it's very useful to like always give variables for certain operation to be like explicit, so that someone that is reading your code will easily understand. So that's why we'll try to type these long words. Great. So now we have our FFT shifted. The next is to compute the magnitudes of those amplitude, the Fourier amplitudes. And this one is just a scale factor that is just trying to just enhance those magnitudes so that we easily visualize them when we're plotting stuff. Let's call that our magnitude spectrum. So basically, it's this shifted FFT results. And the first one is the real component. The second one is the imaginary component. We're extracting the magnitude of this particular shifted FFT result, and we'll take it to a log space. So yeah, it's no longer linear. It's usually better, easier to visualize stuff and in log space once it comes to like the Fourier transform. And then we'll scale it by a factor of 20. It doesn't have the 20. It could be used a big number. The bigger you use, the higher the amplitude will go, and the easier for you to visualize stuff. I'm just using 20 here, just like an example. And I'm going to plot it so that you see what I'm saying. So if I run this cell now, it's going to make, so this is the FFT. This is just the FFT. This is the 0 point. I silent the access, but if I comment that and run it again, we'll see the numbers. Well, it's just the pixel that shows, so that's not very useful anyway. But effectively, it's able to shift this to the middle point rather than having it at this 0. So the FFT itself was 0, but we shifted it to this point, even though the axes are just pixels, because I did not provide any coordinate. Just using imshow. Those that provide x, y. Of those, you would have assigned the proper values to them. And so this is how the transform looks. This is the component that have most of the information on. It's the low component. again, these lines are coming from the edges of the images. So suppose when I tape out the edges, these lines will go away, and then you will just have, as you go far away from this point to any of these directions, you have the higher frequency, the noise and stuff. So this is how it looks like compared to if we just plot it without scaling. So this is the magnitude scaled. If we just plot this one straight up, you see the amount result here, but I think that's a distraction. I'm not going to show you that result here, but just know that this is how the spectrum looks like. Great. Next is to create a mask. Now that we have the spectrum, next point is we want to block out this middle point so that we could just exclude the low frequencies. So we could just keep the high frequencies only for the next processing. To do that, we need to get the middle point of this image. Remember, we shifted stuff to the middle, so we want to know this location. To know that location, if you know this dimension, or know this dimension, if you divide it by half, it will take you to the center. So in coding, that just have to implement the center, basically. So from our image, we get the shape of our image, and that will be the y and the x, so then the row and the column. And then if we divide each of them by 2, it will give you new values, and those values will correspond to the midpoint along each of the axes. And then we could generate a mask, basically from our image, the shape of the image, or you could just do based on the rows, which is just save shape of the image. We are creating ones, and they are of the type of the image we loaded, which is unsigned integer 8. So it's basically all ones, so it's like all ones that look like this. I mean, we could plot that so you could see that. Let me just plot that really quick. It's just do the figure plt the this. You could use p color, we use m show, it doesn't matter. Let's use p color, and then let's put in the mask. We're not even giving the color map. Let's see, we got an error about the shape. Ones of that, okay, they are of 2, so I think this is not important. Let's just leave that. But if you print these values, you could see them that they're all ones. Basically, it's not important what I wanted to do. They're just basically ones, which is what I wanted to show you. And now that we have the mask, we could create a point, a cycle in the middle of that mask. So just basically fill some point with odd zeros. And here I'm defining the variable that will allow us to have more control over how big the cycle will be. You could use diameter, you could use radius. Here I'm using radius of 30. We'll tweak this number. This is the number that will allow us to just detect just the edges or detect everything in the image. So if you make this very big, you then like filter out both the low and the high. If you make it very small, then you filter only a small component of the low frequencies, and then you get to like get your image look more blurry. So I'll play around with this to show you how you get the best result. I intentionally left the effect example I showed at the start to be that way, but we'll work with that. And the next step is create a cycle. Again, if you know the equation of a cycle, your x squared plus your y squared, that is equal to some value, 0, whatever. It will give you some distance, basically. If you know how to code the equation of a cycle, you just create it, basically. So that's what we're doing here, but we're using an MPO grid, and we're putting in up to the row and from the column all the way. That's just from the center, basically, if you're not familiar with this stuff. So we'll get our x and y, and then we could just calculate our cycle and then fill in based on that radius from the middle, based on that distance, fill it with 0 so it blocks the center. So if you run this now, we have successfully created this mask and it has filled in zeros. The next step is to now start backtracking back to the original image. Remember, here we are in the Fourier Transform space, in frequency space, not our physical space. And so on our mask, if we times it with our data, which was the discrete transform that was shifted, then we'll get the shifted stuff. But now we have successfully blocked the center component of those frequencies. So the long ones are excluded in this particular one. Again, if we do the same thing, that the kind of scaling that we did on the other one, just times 2, and in log space on this shifter, we could easily see the filtered one. So this was what I want to show you. I already had it here. So if I run this, it would make a plot. So that's the circle we created, and now we have done everything there to be 0. So basically it could be nans, but nans wouldn't work with FFT when you are backtracking, so we just use 0. So when you use 0, it has successfully blocked the low frequencies. You only have the high frequencies. If you increase the radius, the circle becomes bigger. If you reduce it, it gets smaller, which means that way you have more control over the range of like low and high frequencies that you want to include in your analysis. So that's how you do this. Now we're filtered. We've done what could be called a high pass filter, because we've excluded the low frequencies, and then now we could shift the stuff back. So remember, we shifted it to the center. Now we have to take it back to where it was, and that's through the inverse FFT shift. So we just do inverse FFT shift over this image above here, and then we also inverse the discrete transform that we did on these shifted frequencies, and now we have our image back. So this is our image, our new image that is filtered. You could also just extract the magnitude from these images, this image back that you have. Again, you have the real component, you have the imaginary component, and this finally give you your. So if I run this now, our image back is a final image back, and these numbers are not guaranteed. There's the magnitude in here. Let's just print them. Are not guaranteed to go from 0 to 255. So you have to renormalize them. So these are the numbers that are floats, but they are also numbers that look weird. You have e to the 8 and stuff. They are not like a typical image that will go from 0 to 255. And so to do that, we have to normalize the image. And OpenCV has this normalize function where you put in this your data or your image, and then you tell it the range that you want. So we want it to start from 0 to 255, and then for the method we tell it to normalize based on the min max. So basically it will come here and look for the minimum value, the maximum value contained in this data, and then it will scale it so that it goes from 0 to 255. That's pure math. You don't have to use this function. You could work it based on the math you learned in school, but there's already a function here, so you could also use that. And with that, we'll have our image back, and I'll be plotting the image back and be calling it here reconstructed image. So this will successfully show us the filtered image. Again, this is how it looks like. This was what I showed you before. Now play with this radius. So we had 30. What happens if I change it to 20? Your guess will be it will be what? More blurry, so to make it more worse. So you will not be only detect the edges, for example. But if you make that number bigger, which means the circle bigger, then you have, so this the new one. This is how it looks like. Now I'm going to increase this number to say 40, or let's go all the way to 50, almost one of the critical values. And if we run this now, the new image will look much better. Yep, you can see that the cutting that was at the back, everything is going. We're now just seeing the edges, and if we push that number further, and again this circle will be getting bigger. If we let's move it to say 70, go to 70, and if you run this now all the way to that point, we get our image. You could see the background is completely clean, all those and low components are gone, and now we just have the hair showing up, we have the edges showing up, and again the edges on the shirt showing up, the color of the shirt showing up and stuff, and nose and eyes and stuff. You can play along with that number until you get to the way you want your edges to be, and so that's how you do it. Again, this code I'm going to link drop the link to my GitHub. It's corresponding to this code in the description, so you can always get the code. You don't have to type everything. The code will be available, and it doesn't only work on this image. It could work on any of your image. You could use that way to detect edges in your image. I hope this content was useful. I I'll be making more similar videos that are sort of like on project based or handful tools that you could use in other projects. And so be sure to subscribe and turn on the notification so that you know anytime I post new videos, and tell a friend to tell a friend about my new channel. And please also hit the like button, because that's what tells YouTube that this video has some good information, so it pushes out to other people, and that way you are helping me. That's the only way you could help me actually. Or you could, if you are that much kind, you could also drop a comment in the section below, in the comment section below. Thank you, and I'll see you in my next video. Bye bye.